in doing these proofs. And to work together and to ask us questions. So I want to show you several things. We got through reforming the post office, the postage stamp problem, which was pretty fun. And we also got to look at the process. So, you know, I've actually reproduced this proof for you here. These notes are on the web, by the way, on the course website. And as I mentioned, please take notes before the breakout room so that you can know what the problem is, because while you're in the breakout rooms, you won't have access to these screens, unfortunately. And we started to prove that the square root of 2 is irrational. So let's review what we are. There's actually some pretty interesting and somewhat deep mathematics here. Not deep like it's difficult, but deep like you have been shielded from it before. So remember this, what we had before. We have the natural numbers, which are a subset of the integers. And that's a subset of the rational numbers, which are a subset of the real numbers. And these inclusions are actually strict in the sense that there is at least one, there are integers that are not natural numbers, namely the negative numbers. And there are rational numbers that are not integers because they're not whole numbers. So an example of the first would be -1, which is not a natural number, but surely is an integer. Example of the second would be 1/2, which is surely a rational number, but is not a whole number or an integer. And then, as I mentioned, you probably have been told there are these things called irrational numbers. And those are real numbers, but they're not rationals. They cannot be expressed as a fraction, a over b, where a and b are integers, and b is not equal to 0. And one example of those that you may see in high school or other places is the square root of 2. And most of you have heard this as an irrational number, but how would we prove that? So there are many ways, but one kind of cool way that we can do right now is by induction. We have to be careful because we're inducting it on the denominator of rational numbers of the form p over q. And in these notes, which are available to you now, have been up for about a day, I reproduced what I have before. I have added the base case, which I asked you all to think about. So I hope you tried to prove that yourself. If you didn't, try to prove it and then look for it. So the base case, and we spent most of our time on the induction step. So just to review where we are in terms of this, we spent most of our time on this sort of architectural framework, and now we have to actually put in the actual beams and columns that will construct our proofs, namely claims 1 and 2. So basically, in our inductive hypothesis is relatively straightforward to understand. It says we're ordering these rational numbers, which we assume are lowest terms, so that's not actually necessary for the proof. These rational numbers based on the denominator. So we're counting up by induction on the denominator q. And the inductive step says, look, for all rationals that have a denominator q such that q is less than n, that rational p over q is not the square root of 2. So all the way through and going right up to you know, p over n, p over q is not the square root of 2. Now, what we merely need to do is show it for the next one. So this is strong induction here, obviously, as we mentioned before. So what we need to do here is we need to show for the next one, i.e. just one more than n minus 1, namely n, that p over n is also not a square root of 2. And then so we have a plot to do this by contradiction. So here you have to get the logic right. And this is the kind of thing that if you were doing this, you might have someone guide you in it. But basically, the way that you would do this is as follows. So it's standard induction. We assume the induction hypothesis, which I've written up above here. And now in order to prove this, let's assume the opposite of what we're trying to show. Namely, instead of showing this, we assume its opposite here. Namely, what we're trying to show is that when we set the denominator equal to n, that there's some p such that p over n is a square root of 2. Kind of surprising, right? All the things beneath that couldn't possibly be, but this one would be. So it's surprising that such a thing would be true, but let's assume it. We'll derive a contradiction. It has to contradict something we know or have assumed. When we get that contradiction, we know that the opposite of this last underlined statement here must be true. So in other words, need only show, one way to do this is to say, well, if it's true that p over n is the square root of 2, one way to get a contradiction is to show that there's some other rational number with the denominator smaller than n, such that it is the square root of 2. And that's forbidden because we assume that for all other rational numbers with the denominator less than n, that couldn't happen. So it would directly contradict the induction hypothesis. So in mathematics, we need a name for this other rational number, which I arbitrarily called P prime Q prime, P prime over Q prime. And the only constraint on it is that Q prime has to have a smaller denominator. So basically what the proof architecture says is that if it were true that having assumed the inductive hypothesis, namely this is true all the way up for denominators less than n, that when we suddenly stick n in the denominator, there's some rational number p over n, which is the square root of 2. Now, if that was really true, then it turns out if you really did have a p over n, the square root of 2, what we're going to show today, and you're going to help me prove these, is that if p of n is a square root of 2, then p over something else, then some other rational with a smaller denominator is a square root of 2, which contradicts the induction hypothesis. So that's sort of stated here. Let me just say it again. If p over n is a square root of 2, then there's some other smaller denominator rational that's a square root of 2, which is kind of surprising and weird, but that would contradict the induction hypothesis. And then we're done, because once that is shown, then this thing that we assumed here can't be true. In fact, the opposite has to be true. When you get the opposite of that, you get this thing here, which is what we're trying to do. So we spent a lot of time making sure everyone was comfortable with the general architecture of the proof. And now we have to get into the bones and actually prove this. And here are two claims. So let's see why, again, these two claims would actually demonstrate this. And then I'm going to give you the claims to do kind of one at a time. In breakout rooms, we'll have a discussion. So these are basically technical claims. They're claims about numbers, right? And when you put these together, they're going to give us our proof, basically. So essentially what we're going to have here is something like the following. We're going to say that the first one says that if p over n is a square root of 2, then here's a technical constraint on the number p minus n. It's positive and it's less than n. And why do we care about that? Well, the work is done in claim 2 here. It says if p over n is a square root of 2, then there's another square root of 2. And it has this strange formula here. But when you put these together, it means that this other square root of 2, whose existence is implied by p over n being a square root of 2, this other strange thing here actually has a denominator less than n. And that's what's going to provide our contradiction. So in order to do this, we call p prime and q prime witnesses. They're witnesses to the crime. They show that something is false. I have to actually produce those in a lineup and make sure they're true. So I just take p prime to be the numerator here and q prime to be the denominator, as I've done like that, and the proof is done. Why is it done? Because I've demonstrated that there is a rational square root of 2 with the denominator less than n. That can't happen because the inductive hypothesis assumes it can't happen. So as soon as we prove claim 1 and claim 2, this is done. And the reason that I especially wanted you to see this, not only for the use of induction, is to see the similarity between writing a large program or complicated program and proofs. So what you can do is you have a specification for what the claim should do, which is the statement of it. And if it's correctly implemented, that is proved, then you can use it as if it was any mathematical fact, the same way you can use any subroutine that satisfies a specification anywhere and anyhow in the program without fear. And that's the duality, in sense, between programs and proofs. And computer scientists generally believe and say that programs are proofs and proofs are programs. And this is a little peek into how that works. So with that having been said, what I'd like to do is I'd like to have you go to breakout rooms, and I'd like to have you prove claim 1. We'll come back, we'll talk about it. These are not difficult claims, but they're really good practice. I'll give you 5 minutes for this. I'll start the breakout room in 60 seconds, and then I'll bring you back. We'll ask how you did, and then we'll do claim 2 after that. So bear with me while I do breakout rooms. You'll still be able to hear me, but I'm not going to force you to see me walk across the room. And of course, as usual, if you have any questions, please go ahead and ask me. I realize we're going to go to breakout rooms, but as always, the point of this is to, the point of this exercise is to be able to ask questions. All right, we'll see how this works. So let's go to claims 1 and 2. Let me ask you, who got this and how did you do it?
I think we came up with a solution.
Okay,
So
good.
yeah, what we basically did was for claim one, I mean.
Sure. Yeah, just claim one. That's all we want to do for now.
All right,
Absolutely.
we took the square root of both sides, and then because p and n are both positive, it has to be the positive square root of 2. So then p equals n root 2. And then basically we said that n root or root 2 is between root 1 and root 4. And you can rewrite the inequality by adding n to all three terms, and you get n is less than p, which is less than 2n. And then because we know p equals n root 2, and n root 2 is greater than 1 but less than 2, the inequality is true.
I'm just computing. Yeah, I think that works. It's kind of a direct construction proof. So I think that definitely will work. It's a little different from how we did it, but I think it's good. If you would not mind sending us an email with that, we'll maybe post that for our other students to meditate on, because it's a little bit different from other proofs, which is kind of cool. So good job.
Sure.
Did anyone else have a way to do this that was maybe a little different? And I'm not saying different is better. There are a number of ways to do this problem.
I did a version which was a little different. So I just said straight off the bat that, so since p over n squared is equal to 2, it's between 1 and 4. And then you take the square root of all of the terms. So then you have 1 is less than p over n is less than 2. And again, the square root of p over n has to be positive because all the terms are positive. Times every term by n is less than p is less than 2n, and then subtract n from all the terms. 0 is less than p minus n is less than n.
Yeah, I think that works too. It is slightly different. So send us that as well, and we'll try to type it up and maybe share it with the students, because it's nice to see the other students to see another version of it. I'd like to show you our version, and I don't think my version is superior, so that's pretty cool. But I think it's worth seeing, and then you at least have a record of one of these kind of proofs. If there's a question, where did these claims come from? Two ways to think of it. This is an exercise in doing proofs, and I assign them. The other way is that I came up with these claims as a way to complete the induction proof. So you can think of it as working with a learning mathematician working with a slightly older mathematician who's going to make suggestions on how to do the proof. And we can talk a little more about that later if you like. So let me show you how I did it. I think the proofs we had were good, but this might be worth seeing. So let's do claim one. I'll write it out again so we can think about this. If p over n squared equals 2, then we have this inequality. 0 is less than p minus n is less than n. So I just thought you all might like seeing it done in this fashion. I did two proofs by contradiction. I thought this was kind of cool. So we have two parts to prove, two inequalities. Let's call this one A and this part B, if you will, just to name them. Let's do part A by contradiction. You always say that, by contradiction. So by proof by contradiction, we're going to assume the if part and then assume the opposite of this part here. So we're going to assume what's called the antecedent, which is this part, and assume the opposite of the consequent. If we get something absurd, if we get a contradiction, then we know that the opposite of the assumption is true, and therefore we proved it. So to assume the opposite of this, of part A, sorry about the coughing, we're going to assume that 0 is greater than equal to p minus n. Right, so look at the pattern here. We assume the antecedent. We look at the consequence. We just look at part of it. I'm going to just take this part here. I'm going to negate it and assume that. So basically, I'm going to look at the situation where we have p over n is the square root of 2, but somehow magically 0 is greater than or equal to p minus n. What can happen if that's true? Well, if that's true, then just by simple algebra, we have n is greater than or equal to p, and then we have 1 is greater than or equal to p over n. Now we can square both sides. So if we take this side here and square it, we get 1, because 1 squared is 1. And we have this statement that this is greater than or equal to p over n squared. Well, what's p over n squared? Well, we just assumed by assuming the antecedent that that's equal to 2. This just implies from the if part of the antecedent. So therefore, if we assume this absurd thing here, we can prove that 1 is greater than 2, which is a contradiction. I can't quite hear you. Can you say again? I think
that was an accidental unmute.
Accidental unmute? Okay, no problem. Sorry. I thought it was a plea for help. All right. Would everyone like to see it for B, or would you like to move on to claim 2? B. Short and sweet. Then we'll have to take questions as well. All right. All right. Let's get rid of. All right, so B is going to be the same kind of thing, again, by contradiction. So what do we do here? Well, we're going to assume the antecedent again, namely assume that p over n is the square root of 2, and we're on to B. So we're going to take this part here, and we are going to assume that is not true. So namely, p over n is the square root of 2, but somehow magically, weirdly, counterfactually, p over n is greater than equal to n. This is an n here. P over n is greater than or equal to n, right? Put a star there, which is my way of saying I don't really believe that. It's only assumed by way of contradiction. And there's a mathematical thing you'll see the TA sometimes do, BWOC, by way of contradiction. So assume by way of contradiction. This means you assume it, but you're going to disprove it. So if this is true, again, we have a little bit of algebra. If that's true, what happens? Well, we can just rearrange and say p is greater than or equal to 2n. And then we can divide both sides by n and say p over n is greater than or equal to 2. That's pretty cool. Now we can square both sides. No problem. P over n squared is going to be greater than or equal to 4. So no problem yet, except that up here we assume the antecedent. So p over n squared is equal to 2. This is just from the if that we assumed. Therefore, we have just proven that 2 is greater than or equal to 4, a contradiction, and therefore we've proved claim 1. What do you think?
I'm a little confused on where we said above that 1 is greater than or equal to 2.
Right here.
A, yeah.
Yeah. How can I help?
Why is it technically 1 isn't greater than, or is it because it's contradiction we know that it's wrong?
Well, if I assume this, then I can prove that 1 is greater than 2. Since that's false, therefore my assumption here was false, because it's the only thing that I've assumed. Great question. And similarly down here.
Oh. Hi, so I get in an informal sense why this is allowed, but like formally, why are we allowed to assume that p and n are natural numbers and not integers as from the definition of rational numbers?
Oh yeah, it's suffice. You're absolutely right. They're just positive. I mean, they have to be positive for this claim, and you need another little claim to make them negative. But it would be pretty strange, right, if there was a negative number that was the square root of 2, negative rational number, right?
Okay, so like if we encounter a claim like this that we want to prove, we're like obviously like,
yeah,
heuristically I can say like, yeah, they would have to be positive. Do I need to like prove that in any way?
Well, we're not going to ask you, if we asked you to prove, we could easily ask you to prove things of complexity of claim 1 and claim 2. We're not going to ask you to prove that the square root of 2 is irrational on a test. if you wanted to do this, you would have to say in claim 1 that P and N are, let's just be conservative positive integers. Like claim 1 only holds for positive integers.
Okay.
And then I only need it to hold for positive integers to make my proof work. And that's something that you can go off and prove pretty quickly. Like, so suppose I just added to this, which I should actually, I should say, for all P n natural numbers greater than 0, right? So now we're totally fine on this page, right? Because P and N are natural numbers that aren't 0. Now you need to go back and convince yourself that that suffices for the overall architecture of the proof. But that isn't really that difficult. Basically, the argument is if just one of them is negative, then you have a negative number, and you'd be trying to prove that a negative number was the square root of 2, which would quickly lead to something false. If they're both negative, then it's the equivalent to saying they're both positive, and you reduce to this case. But great question, and always good to get those assumptions very clear, and always good to ask those kind of things because you know, someone could have missed something. Are you happy?
Yep.
Good. Any other questions?
Why does P over N squared equal 2?
Well, it doesn't. But suppose it did. Like an if statement is always phrased as if something, then something else. I'm always allowed to assume the first part and see what the consequences of that are.
And so is there a reason you chose 2, or that was arbitrary?
Well, it's 2 because see, the thing is that these claims, these particular claims are of no interest except in the service of the larger proof I'm doing. They're kind of like anonymous procedures, right? They're just things that I need, technical lemmas that I need to prove my big theorem that square root of 2 is irrational. So the reason it's 2 is because I'm trying to prove something about the square root of 2.
Gotcha.
Right. So this is another way of saying, I mean, this is the way we say this in mathematics. We can't really say the square root of 2 equals 2 because that's kind of a, I mean, in some sense, informally, this means if the square root of 2 equals 2. And what the perspicacious student will realize is that, you know, I mean, sorry, square root of 2. Well, so it doesn't quite mean that, you know, it means that if the square root of 2 is exactly a rational number. I'm sorry, I'm having a little trouble encoding my intuition here. It means that P over N equals the square root of 2 is what I meant to say. Sorry. That's kind of informally what this means. It's just that this is kind of a strange beast because you can, I mean, it's perfectly reasonable to say it, but it assumes things like that the existence of the square root of 2 and the fact that you can clear denominators and things like that. So I think this is a clearer way to say it. It says it's a rational number that when squared gives 2, which is kind of the definition of square root. So it's just kind of a mathematical preference.
Okay, thank you.
But that gives you clearly the connection. If you realize this is a formal statement of the somewhat informal statement, P over N is the square root of 2, right, which kind of doesn't make that much sense. You can see the connection. I'm proving something in the big lemma about the square root of 2. That's why the 2 comes in there. But great question.
I have a question clarifying something.
Sure.
So for the claims, I can understand we're trying to prove things depending on the if statement because we're trying to do a proof by contradiction, but we're not expected to be able to generate the later half of those claims by ourselves, correct? Like we're not supposed to have the intuition to generate that ourselves right now?
Well, we've given you 3 proofs of these claims in this lecture alone. Any one of those would be sufficient to prove it.
I mean, like if we came upon the problem of trying to prove that the square root of 2, like if we came across this proof outside of a lecture scenario, then like, should we be able to find the later half of these? Should we be able to make these claims by ourselves? If that makes sense.
Come up with claim 1 and 2?
Yes.
That would be probably difficult, like maybe by the end of the class, but not now. You know, maybe after you reflected on the class. But no, I'm not going to ask you even on the final to prove the square root of 2 is irrational.
Okay, thank you.
Yeah, yeah. This is about understanding I mean, it's a great proof to memorize because then you actually know some mathematics that most people just take for granted. But I don't see any value to having you just reproduce this verbatim on an exam, and related things in this family are a little bit difficult. But there are some proofs that we will get to that will be routine that are somewhat more complex than what we're doing now. So you could be expected to be asked the kind of things you're seeing on problem sets and short assignments up to now, and that will gradually increase in complexity. But this would be a level of complexity beyond that for you to generate. But I think being able to prove claims 1 and 2 are reasonable kind of things. I probably wouldn't ask you something totally unmotivated, like prove this bizarre claim about numbers. It would be in some other context. More questions?
Yeah. So when I was talking about the proof by construction, I think you called it, I took the square root of both sides of p over n squared equals 2. And you said that you can't really do that because it's sort of informal. So would that proof, like by construction, still hold up, or would you not be allowed to do that?
I would allow you to do it. It's just kind of not how number theorists usually think about it.
Okay.
Really, because the reason is more that this is really a taste issue. Is if I say p over n squared of 2, that kind of gets into some confusions. Like people wonder, well, what's the representation of the square root of 2? Is it some platonic object? Is it a floating point number that's an approximation? Is it an infinite non-repeating decimal of some kind? I mean, what does it really mean there to have equality? And how would you check for that? Basically, we kind of haven't yet in this class talked about a decimal representation of real numbers, although I will get to that in lecture 13. And you kind of need a representation like that to kind of make sense of this. So basically you need 2 parts to really make that formal. One is you could do it as a decimal expansion, which has its own problems, but is actually fairly rigorous. You could also do it by talking about what are called the algebraic numbers. So these are numbers like the square root of 2 that are defined by being the roots of some polynomial. And once you've defined that set of numbers, then you can do things like that. I would totally accept that on a proof. I'm just saying that I would prefer to see it the other way.
Yeah, and then sort of going off of that, the other student brought up another version of the proof where you just, instead of having to solve for n, you just put in p put in p over n is less than root 4, but is greater, I forget the exact terms of the proof, but would that actually work better because it doesn't actually make you like take the square root and solve for p equals n root 2?
Well, I actually think your proof is fine. It just relies on some things so basically when people come into this class, they've been shown some stuff before. And as we've seen, a lot of the stuff that they've learned actually is great, just they haven't really been told why it's true. And other things they've been told are utter nonsense, and we're trying to correct that. But in this particular case, your knowledge of decimal numbers and the square root of 2 and things like that is not, it's not wrong or off. It's just that I would like to just see it be a little more formal before we use it a lot, and we'll do that in this class. But nothing's wrong with it. I don't think the approach of the other student is necessarily better. I think they're kind of equivalent in rigor. I've called it a bounding argument, and bounding arguments are perfectly decent ways of proving this. So pending checking these carefully, because I'd like you all to send them in for us to look at. I think they're all 3 good proofs.
All right,
and different proofs too, which is kind of cool.
Thank you.
Good, great questions. More questions? Great discussion. All right, well, let's go to claim 2 then. I'll start the breakup rooms and then I'll write it down and you can look at it in the last few seconds. And I'll bring you back in 5 minutes as before. Okay. Well, let's write it down real quick here. So claim 2. I know you have this, but it's kind of nice to have it here. Again, if p over n is the square root of 2, then this strange thing happens here. 2n minus p over p minus n squared is equal to 2. I have another square root of 2. There we go. All right, I will go over here, start breakout rooms. Again, we'll start in just a couple of minutes here so that you can go to breakout rooms. I'm going to open all rooms, and I'll see you in about 5 minutes. Good luck with claim 2, and we'll have a discussion about it. All right. All right, it looks like we're back. I was wondering who has a solution they'd like to discuss to claim 2. We can talk about that.
I can go over just an algebraic proof.
Yeah, my proof is pretty algebraic, actually, although there are other, I think that if all goes well, we might show you a couple of different ones on the web afterwards. But what's your algebraic proof like?
Well, I took p over n, and here it might be easier if I like show my paper, and then I multiplied it by the fraction of p minus n over p minus n over n.
Yep, that's what I did.
Yeah,
that proof works. Yep.
Okay, yeah, it's that thing.
That's good. That's good. That's a good proof. Well, I think I know your proof because it's similar to mine, so I'll definitely show that at some point. Does anyone else have another idea how to prove this? That's a very, very nice proof.
So I haven't gone all the way yet, but I thought maybe you could substitute the 2 for p over n squared, and then sort of simplify that down. And I've
That's
gotten as far
possible.
2n squared equals p squared, but I'm not sure where to go from there.
Yeah, I think that leads somewhere. So let me show you the proof that your colleague came up with, which is, I happen to like it because it's similar to mine. I think yours might work too, and we'll today or something, I'll post a similar proof to that. And if you get it, send us yours, and we'll put those on there. So we're very interested in seeing your proofs, and if they work, we'll post them so people can see the diversity of things. But let me do the first proof. Well, does anyone else have any ideas about this? Or would you like to see a proof and how it's done?
I think I have pretty much the same one that whoever just talked said, but I worked it out, so it does work eventually.
That's good. Would you send that to us? We'd like to see it, and we'll check it, and we'll share it with the students so they can see a number of different proofs. That would be great. Send it to me and the grad TAs, for example. We'll circulate it, and we'd love to see it and look through it. So good job doing that. Let me show you one proof. I think it's very similar to the first one we saw. So my proof starts with, I need only show that p over n is equal to 2n minus p over p minus n. That's the only thing I need to show you. Does everyone see why that's true? All right, so some questions on this. So remember, need only show is a sort of modular way of thinking about things, right? So I'm going to write a subroutine that, delivers this. So remember, the statement of this theorem, this claim, is that if p over n is the square root of 2, then this other thing is the square root of 2. Well, in this scenario, we're assuming a world in which P over N is the square root of 2. So if I have already shown that P over N is equal to 2N minus P over P minus N, so let's, then I just assume, so if I say assume P over N is the square root of 2. If I take this assumption, and if I take this fact, then I can substitute this into here, and I immediately get the consequent. And that's why it's sufficient just to show this. I haven't shown it yet, but that's my proof plan. What do you think? Do you believe that argument?
Yeah.
Any questions about that? Okay, so let's just do it. And this is very similar to what my colleague put up recently, the first one. So let's take P over N. What's this equal to? Well, that's equal to P over N. Let's multiply it by P minus N. But we have to make sure we haven't changed anything. So P minus N in the denominator, right? So that cancels out. So this cancels out to 1. So that's why we have equality there. So that's the trick. You have to multiply the top and bottom by something. And how did we see to do that? Well, we kind of want a P and N in there. That kind of give us the idea. Now we just a matter of simplifying, doing some algebra. So that's just equal to P squared over N minus P over P minus N. And now we can rearrange a little bit. We can get P over N squared times N minus P over P minus N. But look, the if part of the statement says if we can assume that P over N squared equals 2. So this guy here is equal to 2, and now we get 2N minus P over P minus N, and we're done. Did I represent your proof correctly?
Yeah, I did. I mean, I wrote the steps down differently, but like it's exactly the same algebraic thing.
Right. Okay, good. So we have a proof. Well, I would say we have this. We have a solid proof of claim 1, solid proof of claim 2. We have some proofs that have been described. I'm sure that your proof is pretty similar. I'd like to see those just because we will share them and we can all learn from them. So send those. Email is good. And we will probably vet those and post them on the website. Right. Any questions about proving claim 2? All right. So you all have been, and we'll actually, it looks like we're going to post a third proof of that, so you can see different ways to prove this. All right, so you all have been very patient. We've proved all this stuff. We've now proved rigorously that the square root of 2 is irrational using induction, which is pretty cool. So let's have a little fun. So one of the things is that we've been showing you proofs that are correct. I mean, they're correct unless I make a mistake. And then you guys are like eagle-eyed, you catch it. It shouldn't be like that, right? And that's good. But what if one of the things that's going to happen is that you're going to be shown proofs that are incorrect. Might be your partner, might be someone else, you might be a TA, might be in your research group, might be in your engineering project. How do you know that? Like, what does an incorrect proof look like? And how can you argue that? And some of these are actually quite amusing, at least to a mathematician. So I'd like to show you some proofs that are incorrect and have you spot the error. All right. So here's a pretty fun one. Theorem. All horses are the same color. And I'm going to prove this by induction. Prove it in quotes, because obviously you can't prove this. Now, I could also, and they'll do this in your next algorithms class, you could also prove that every horse has an infinite number of legs. I'm not going to do that. But a corollary of this proof, corollary, like a little term that follows, is all CS 230 students will get the same grade. And another corollary is that you don't want that to happen because someone might not get a good grade. So now we're motivated to find out what's wrong with this proof, because maybe you're not a biologist and you don't care that we've falsely proven that all horses have the same color, but you might care that all students will get the same grade in our class. So I want to mention I'm going to use induction, but this is not a proof that shows that induction is wrong. It shows that we've made a mistake somewhere in using inductions. Okay. So I'm going to do the proof and I'm going to ask you all what's the problem. Proof in quotes. This will be by induction on n, which is the number of horses. And our property P of n is in a set of n horses, all horses have the same color. And here's my base case. My base case is n equals 1. Well, if I have a set of n horses where n equals 1, there's only one horse. The same horse is the same color as itself, and therefore all horses have the same color in a set of size 1. So we're done. Now the induction step. I should say this is a false theorem. So I want to assume any set of n minus 1 horses are same color. And of course, this will be my induction hypothesis. And I need only show any set of n horses are same color. So here's my argument. Here is my set of n horses here. Obviously it's discrete, but I'm going to draw it like this. And I'm going to take, I have n horses in this set. I'm going to take out one horse. And I'm going to give him a name. This horse is called Mitch. I don't care what color Mitch has. But now I'm left with a set of, this is n horses. I'm left with a set here of n minus 1 horses. And there are a bunch of horses in here. And by the induction hypothesis, all the horses in this set of size n minus 1 have the same color. And so, for example, if there's some horses in here, here's a horse called Ted, and here's a horse called Jim, then there are just two of the horses in this set of n minus 1, and they have the same color because by the induction hypothesis, clearly stated here, any set of n minus 1 horses are the same color. So now what I do is I put Mitch back in, and I have a set of n horses again. And now I'm going to take another horse out. I'm going to take out Jim. And now again, I'm left with a set of n minus 1 horses. And by the induction hypothesis, all horses in any set of size n minus 1 have the same color. And therefore, for example, two exemplars in there, Mitch and Ted, here have the same color because they're in a set of n minus 1 horses, which are all the same color. However, same color is a transitive property. And so Mitch has the same color as Ted by my recent argument. By my previous argument, Ted has the same color as Jim by my previous argument. So therefore, Mitch, Ted, and Jim all have the same color, and the choice of Mitch, Ted, and Jim are completely arbitrary. And so I claim we have a proof that all horses are the same color. Okay. So what went wrong? Do you believe that all horses have the same color? Or do you believe I made a mistake?
One thing that can go wrong is that, so you don't necessarily have, I guess to describe it, like a set of horses that the color property can transfer through. So for n equals 2, you do have you can generate two different n-1 sets with the same color horse. However, there are no horses in common. There's no intersection between the two sets for n equals 2 that allows the color property to be like equivalent between the two n-1 sets.
Yeah, I think that's right. I think you put your finger on what the problem is. So, so basically, to summarize your argument, the base case is actually fine. N equals 1 is true. Set of n equals 1 horses has the same color because every horse has the same color as itself. But you can't actually induct. So n equals 1 is fine, but you can't actually induct from 1 to 2. Like it fails for 2, exactly for what reason you said. So in the case that you have n equals 2, I'll just draw out your argument. There are other arguments against this as the primary one. So now I only have 2 horses in here. Say I only had horse Mitch and Ted. Well, everything is sort of fine there. I could take Mitch out. I'm left with a set of n-1, namely 1 horses that all has the same color as himself. That's Ted. That's fine. When I reverse this, I get the same situation here. Everything is consistent, but there's no transitivity property because I need at least 3 horses for transitivity. So basically what happened here is I set up a good base case, but you can't actually induct from 1 to 2. So it doesn't work for 2. So this proof is actually not correct. And actually, if you go to Shackelford Banks, you can see horses that actually have different colors. All right. So it's important to check these proofs carefully because you can make mistakes and others can make mistakes. And just because it uses induction doesn't mean it's being done properly. Any questions on this proof with a bug in it? And I hope you see why I'm showing you proofs with a bug in it. First of all, if you're a mathematician, it's hilarious. But even if you're not a mathematician, it's good to see proofs that don't work so you can see common mistakes that people might make. Any questions on this bogus proof? All right, let's go on to a different kind of thing. I wouldn't say this is completely bogus, but I'm going to ask you. So in this case here, it's clearly the theorem has to be false, right? Because we've observed horses. We have empirical evidence against it. Very surprising. So we see the theorem is false. We look for a proof, that a problem in the proof of some kind. So that's the exercise there. So one thing you'll encounter, instead of just, oh yeah, he's doing a proof, I can zone out now and look at my phone, because he always proves stuff is true. Someone could prove something incorrectly, right? So we want to understand when proofs are wrong. But what about something like this? And here I'm going to ask you whether it's a proof or not. It's going to be a true fact. So in this case here, we used induction and proof techniques incorrectly to prove something that is actually false. So a false proof cannot prove correctly a false statement. Well, what if we take something that we know is true or have been shown is true, and we try a different proof of that? Let me ask you if this is a good proof. So I'm going to go back to your calculus and look at the formula for integration by parts. Very useful. Use it in engineering all the time. Okay. So now we have our integration by parts. Let me ask you a question. You can just shout out an answer. You can text, you can chat it. When you saw this in calculus, did they prove it for you? Or did they just say, this is a useful formula, go forth and be fruitful and calculate? They didn't prove it. Right. It's not that hard to prove, but usually they don't in calculus classes. They did prove it. Okay, excellent. So you probably saw some proof that involved rationalization and limits and things like that. So let me give you a purported proof. And the question is, I'm gonna ask you whether or not this is a valid proof. All right, so suppose I have, so it's a true fact, and some of you have even seen it proved, which is great, others haven't. So suppose I want to graph these functions here, right? So I'm gonna call, this is axis V. I'm gonna look at this integral here. And this is the function u, and I have something that goes up like this, right? And the integral under this curve, this thing here, this is equal to the integral of u dv, right? So that's the function u, v is the variable of integration. All this area under here, that's the integral of u dv. Now I'm going to do something I could never do with the blackboard. We'll see if it works. In the history of this class, this has never been done before, so it might not work. I'm going to rotate the paper like this. So now over here, I have u, like this. And I'm going to complete the box like this. So this thing here, now I'm looking at it, look at my formula over here. I have the integral of v du, right? So this thing here by this argument, this thing here is the integral of v du. I just rotated the page. Now we'll rotate it back, make everyone dizzy. So now the variable of integration is v. This integral here is the integral of u dv, which is this part here. Looking at it this way here, the variable integration is u, and this area here is the integral of v du. Well, the area of the whole thing is u times v. And integrals are about area. So this just says, if we want to know the integral of u dv, which is everything under here, we just take u times v, which is the area of the entire rectangle, and subtract from it this thing here, which is the integral of v du. So we have a theorem that we have been told is true, so we've even proved it. And I've given you something that some people would claim is a proof. Have I proved the theorem? Do you buy that proof? Do you believe it? Do you think I've proved it? Is it a valid proof of this fact? What do you think?
So, when you're integrating, like for example, u dv, you're not like literally choosing a box on the graph for the area. At least, like, I don't know if this is a valid counter argument, but like uv as functions, you can't like define a box of area like that because you're only integrating in one dimension.
Yeah, I think you're onto something. Let's get some other opinions. What do you all think? So we'll come back to that complaint. What are some of what do other people think? So if someone gave you this proof, would you believe it? We have one person who wouldn't. What do the rest of you think, and why?
So something I'm not quite sure about is assuming we'd be looking at the second, so the integral of v du, right? So that area. Now here, like you can see it a bit on the function, but it could be that we don't have a continuous function, right? So that the area computed would not be equivalent. So if the normal curve goes down, right? There's like an area where there's like a small section where the area is not computed correctly, if that makes sense.
Right. So I think this is a continuous function, but I think the problem is that the function isn't what we call injective. It isn't one-to-one, right? Like you can't have this happen here. You can have this. You can have two values for you, right?
Yeah.
That's your argument. Yeah, we call that a failure of injectivity, or not being one-to-one. Right. So we'll get to this a little bit later. So if we have a function f from b to u, we say f is injective. This will be like lecture 15 in this class, but it's in your set handout already. If, let's see, f of a equals f of b implies a equals b, right? So it means you only have, we have sets like this. This is u drawn another way. This is b drawn like this. This is your function f. It means if you have two distinct points here, say a and b, they have to land here as two distinct points, f of a and f of b. You can never have them land on top of each other. So that's a technical failure for sure. And I think that your colleague who mentioned a problem with u and v had a problem too. So the issue, both these issues are actually serious issues with the so-called proof. So failure of injectivity, and we actually can see we don't have that here. And by the way, if you don't know what injective is, it's in the set handout, and we'll do it rigorously in lecture 16, I believe. The other thing is a type issue. So I've been using here informally, and I don't believe this is a proof, by the way. This is a figure. Here, u and v are the product of two scalars. That could give you an error. I mean, that's how I'm using them, but that's not really how it's being used. If you think of what u really is, u is some function, lambda v, and it does something, right? And v is some function, lambda of u, right? So these are things of type procedure. So u times v in this sense actually means u of x, well, u of x times v of x, right? So it's a product of two functions. So it's not exactly doing area. So I would say that both of you all, and I'm sorry I made you wait, that had reservations about why this worked, are right. There's a technical reservation about injectivity that can actually be fixed. But this other reservation about types is different. U times V being the product of two scalars to get an area of a box is very different from the product of two functions, which is being done here. So this is a type issue, and it's one, of course, that's nicely resolved in scheme in some sense, because we know what it means to have the product of two functions, right? We can write a, if we want to have the product of two functions, we can say define product to be a function that takes in f and g, where f and g are functions, and returns a function lambda of x, which is the product of f applied to x and g applied to x, right? So we could, for example, say the product of lambda x plus x1 and lambda x squared, right? And this would multiply the two functions x plus 1 and the function x squared. So this is a very different beast from something that's just taking two things, u and v, and multiplying them, where u and v are numbers. So one of the things that's interesting about this so-called proof is that you have some machinery now to talk about it. You actually know what functions are, and you know what it means to have a high-order procedure that takes the two functions and gives you their product. So in this creature here, just as our colleague said, u and v, this operation here, this is a higher order function that takes in two functions, u and v, and returns the product. And you can see here what that would look like in the lambda calculus, which I just made up here. Or you can do it mathematically. So basically what we're doing is kind of a pun. We're using it to represent the area. So I would say this is not a proof. There are several other arguments against it, and you've found two of them, the two most serious ones in some sense. So good job. Now I'll close with an anecdote, which is different fields have different standards of proof. So, mathematics is taught very differently at different universities. And when I taught at Cornell, where I was an assistant and associate professor for about 10 years after graduate school, they had decided, the math department had decided they didn't want to really teach calculus anymore except to mathematicians. And so every department that wanted to have math taught their own version of calculus. So mechanical engineering, electrical engineering, chemical engineering, biology, chemistry, biostatistics, theoretical and applied mechanics, and so forth. And as you might expect, theoretical and applied mechanics, which is a very rigorous mathematical department, had a pretty good calculus program. And generally the professors would rotate through and occasionally teach the calculus for engineering course that was specialized for their department. At Duke, our department is much more Catholic, and math will teach math to anyone. But at any rate, I had seen this pseudo proof and thought it was a pretty funny joke. And I brought it up over lunch once with my colleague who was teaching calculus to a mechanics audience. And he thought it was great. He actually thought it was a rigorous proof. And what he meant was that these equations are hard to understand. And if you have a mnemonic for remembering why it might be true, you might remember the equation and be able to apply it. So opinions can differ about this. To a mechanician, even a very good one, possibly this would look like a proof. To a mathematician or computer scientist, not so much. We have a different standard of rigor. But mnemonics are still good. I mean, I guarantee you that if you think about this, you'll never forget the equation for integration by parts anymore, because you can go back to the silly figure instead. So let's go back and just summarize. This is not a proof, and the theorem is false. So here we have a false theorem of a false proof, which adds up to nothing for horses, because horses actually can have different colors. Here we have a correct theorem if we appropriately parameterize u and v and define everything. And we have a non-proof. It's not completely bogus, but it's not a proof. It's a figure that might be a mnemonic for remembering what these things are, but it's at most a sort of cartoon. So what I wanted to show you is that there are many forms of argument, and what we want to be able to do is write correct proofs. We'll mostly use induction, contradiction, structural induction coming up. And be able to write them and recognize that these are correct, and also be able to spot arguments that are not good arguments, that are false arguments instead. So I wanted you to see these as well, and also they're kind of part of the mathematical lore of how we do things. So we're a minute or two over. I'm going to stop the recording in a moment and take questions, but I want to mention that now that we've had some more practice with induction, and you'll have a little more of this practice coming up, that we will be ready on next Monday to learn structural induction, which will give us a way to prove that our programs are correct, even if they take in list trees and other data structures. So with that, I'm going to stop the recording.